Today we are going to take the very fundamental argument of quantum mechanics. We are going to talk about the quantum entanglement, and we would like to take it away from the laboratories. Quantum entanglement. Okay, this is something that we would like to talk about, and we would try to take it out of our laboratories. And to start with, the argument is like this: that when most people, most of the audience, most of the people hear the word entanglement in literal sense, what they do is they imagine that these things are happening in the laboratories, and people are performing those experiments, and they are entangling the particles. They use lasers or they use some kind of chambers, vacuum chambers, and they test the reality of entanglement, and physicists are arguing late into the night that performing those experiments and arguing that they are not basically imagining cells. They do not imagine cells. They do not imagine the biological entities. And what they perceive, they don't imagine enzymes, but they are doing the experiments that are purely abstract in sense, and they do not imagine the living matter. And yet life is built from the same particles that they are testing in the laboratories, performing those experiments based on lasers, bringing down entanglement, that obey the same quantum mechanical laws. The cells, the biological cells, the biological entities. So the real question is not whether entanglement exists, or I should say that the question is, can life ever make use of this entanglement? As we quietly understand what entanglement is, if you have two particles interacting and they can influence each other quietly, briefly, and without any intention. So that's what we are going to talk about today. We are going to talk about this entanglement. We will try to link it to the biological systems, because entanglement is very weird. And we should start with the very first question: what entanglement actually is. And this is what we would like to learn. This is what we would like to understand. And we would not like to incorporate any kind of mythological argument in it. Let's try to grip this. Let's try to realize the entanglement of exaggeration, entanglement that you have among the quantum mechanical particles. Entanglement does not mean, this should be the point where from we should start. It does not mean something like what we call as telepathy, teleportation, that you can teleport a particle from one point to another point. Or it's not It's not that electromagnetic kind of instantaneous kind of communication going on between the particles. And, and there is no control at the distance. What entanglement means is, I can describe it this way, that entanglement means a shared description. How can I put it? How can I treat it? I mean, take the two particles, not only the two particles, take two or more than two particles. And these particles they are described by one combined quantum state. You can describe two or more than two particles by a single quantum state. And mathematically arguing about it, what mathematically means, they mathematically cannot be separated from each other. I'm just saying it from mathematical point of view. So mathematics dictates me that these particles cannot, this quantum state of all these particles cannot make them be separated, even conceptually. Let's try to understand it. Let's try to understand it with an example. Suppose we have a pair of gloves, okay? So a pair of gloves, right and left. Now, let's assume that we have a factory, and this factory is producing gloves. You start with an argument that you have a factory, this factory is producing the gloves. And there are boxes. Each box contains two gloves. One is a left hand and another is the right hand. So you have a factory manufacturing the gloves, the pair of gloves, they put them in the boxes. And these boxes in which you have those pair of gloves, all of these boxes are sealed. Now what you do is you send one glove to, say for example, to Tokyo, and another gloves you take it to any of the states of our country. So let's assume that the another point is the Bangalore. The moment someone opens the box in Tokyo and he observes it as a left gloves. So what does it mean? It means they instantly know that the gloves that is in Bangalore, that's in Karnataka, is right-handed. It's a very simple kind of example that we can take on. So between the two, nothing traveled, but you can predict exactly what's on the other box. Nothing has traveled from Tokyo to Karnataka. Nothing was sent. No communication. But the information was already structured. The information was already structured in the box. And this is what you can take as an example to understand what entanglement means. Now let's try to understand this. We have this example in our mind. So what happens here is that entanglement works like this. And if we try to go deep into this argument, the properties are not decided. They are not decided until measurement, until the measurement is done. And before observation, you are not observing. Before observation, the system exists as a single entity. You have a single description of the system. Life cannot send information this way, but life may benefit from the correlated outcomes. This is what this example explains us. And there is another important argument, that is non-local correlations in molecular systems. So what does that mean? Now, if we look at the molecular scale, we chose an example of a pair of gloves. Now, if we think at the molecular level, if we think at the molecular scale, electrons are not owned by individual atoms. They are not owned by the respective atoms in your systems. They are shared. They are entangled. They are shared electrons. And shared electrons can become correlated. They can be correlated across a molecule made of many atoms. And this kind of thing is not exotic. This is not exotic. This is pretty ordinary. These things are ordinarily happening at the molecular level. And these things are viewed purely quantum mechanically. These systems are realized quantum mechanically. Let me take you to another example to get a deeper understanding of this argument. You have a suspension bridge, say for example. You have a bridge, okay? Suspension bridge. Now, you imagine that you have a long suspension bridge. Now, steps on the one end, walking on this bridge, the steps of the one end and the cables tighten elsewhere. The cables find the force elsewhere. And this is not because of the communication. If we think classically, we have a classical reason to explain it, but we are taking this classical example to understand our quantum mechanical entanglement. But because the overall structure from one end of the suspension bridge to another end of the suspension bridge is it's one entity, it's a system. Now, can I go to the biological system from here? Now, if you have a large biological molecule, a biological system, say for example, if I talk about the proteins, if we talk about the nucleic acids like DNA, and these were very complex molecules. And if we talk about the complexes, the pigment complexes that you can have in the plants. So what is happening in those frame domains? Electrons are forming the networks. These networks are not based on communication. They are based on their correlation. A disturbance in one region affects the probabilities elsewhere, affects the possibilities elsewhere. This is what we call as non-local correlation. This is what you can label as non-local correlation. Taking the example of this bridge. And in non-local correlation, there is not any kind of signaling. But still, it allows the biological systems to respond. And it allows the biological systems to respond coherently. It allows biological systems to respond without separate individual instructions. What it does, it dictates things in terms of entangled states. So we have entangled states in the biological phenomenon. We have entangled processes in the biological systems. Now, we would like to move carefully towards the evidence of the argument. And what evidence suggests us? What evidence suggests us is that the brief entanglement, it may occur. And the very reputed example that we have is the photosynthetic energy transfer, which I have talked a couple of times before. The transfer of energy, the solar energy into the energy that's needed in a plant. And what you have electron transfer. You have the transfer of chains of electrons. You have a radical pair mechanism. You have a mechanism especially where electrons move together. They move in an entangled sense. And how could we understand this? And for this, let me quote an example. The example of two ice skaters. Okay, you have two ice skaters. You imagine that you have two ice skaters. And what they do, they are holding hands. And they hold hands and they are spinning. Two ice skaters holding hands and spinning. Now release them. Release them suddenly. Even apart. You release them, they are apart, they are away from each other. Their motions remain correlated. The motion of one person depends on the motion of another person. This is what correlation means. And how can we explain this? How can we understand this? I think this is how biological entanglement behaves. There's a correlation. The motion of one particle can be dictated by another particle without any communication. Particles interact and they share a common quantum mechanical history. Now, if they have the same quantum mechanical history, you separate them. And when you separate them, the correlation they have had, it lingers. It lingers even if you take them at infinity with respect to each other. It lingers. It lingers briefly. And life exploits that brief window of correlation. The biological life exploits this correlation. And to go in deeper understanding And let's take another example. An example, say we take an example of teamwork without talking. To understand it, you probably think of two experienced surgeons. You have two surgeons, they are very much experienced, and they work side by side. You have a surgeon one, you have a surgeon two, maybe they are operating something, maybe they're cutting something, and they're not speaking to each other. Now, without speaking, without communicating, the motion, the movement, and the space, the movement of one surgeon acting on a system, and the space, the other. And this is not because they communicate constantly. They are not talking to each other. But the actions, the shots given by one surgeon are dictating another surgeon what to do. But because they share training, they share timing, and they share the structure. We want to understand this. What am I trying to tell here is, how can I correlate it to the biological entanglement? Because here I am claiming an entanglement that's happening at biological level. A biological entanglement is similar in spirit. The biological entanglement is a shared preparation. The biological entanglement is a shared constraints, shared outcomes. No messages, no electromagnetic waves, no sound, no, just coordination. The coordination of one surgeon with another surgeon. Okay? Maybe we understand it to some point. Now, information is transferring, but the information is not transferring in terms of the classical signals. So you have to call some kind of information transfer. And this part matters deeply. We are not claiming that there is any kind of classical interaction. Entanglement does not carry usable messages. It doesn't carry those kind of messages, the limbal messages. And what we can say here is that the biological systems cannot transmit commands here. It's not like giving a signal to another cell and telling it to do something. No. Transmitting meaning. There's no transmission of meaning. There's no transmission of instructions. What entanglement provides us, what entanglement is, we may call it as reduced uncertainty. We may call it as correlated probabilities. We may call it as efficient coordination. But there is no classical kind of transmission between the two particles. That's not something that's going on to happen here. Let's try to understand it more deeply. Let's try to, if I tell you that, you imagine that there are many metronomes. There are many metronomes, and they are set to the same rhythm. But before you separate them, before being separated, and later when started independently, first you have a rhythm, then you think in terms of them independently. They tick in synchrony. Let's take this example and let's try to understand this. Basically, no signal is exchanged. There's no signal exchanged between them. The synchronization that you have, the synchronization comes from the sheer initial coordinations. Your initial coordinations happen to be shared. And maybe life is exploiting this kind of thing. Maybe life may exploit simple quantum correlations. Maybe it's exploiting already these quantum correlations to bias the independent outcomes independently, as if it's a signature. And why this thing helps biology? Why this argument helps us to understand a little bit of it. In complex environments, when you think about the complex environment, you immediately think about the randomness. And randomness is costly. Randomness is on a lot of cost. And entanglement can reduce this cost. Because entanglement is not trial and error. It's a correlated work. It's a guided energy flow. The flow that you have is not random. It's not hit and trial. So it improves the reliability. Even if it lasts, even if it lasts a billionth of a second, even if it lasts trillionth of a second, the action that it does in an entangled fashion, and you have these actions across billions of events, and those small advantages happening at very, very small scale of time, they certainly matter. They seem to be guided. If I talk about the boundaries, and if I think in terms of drawing the hard lines, now think in terms of the boundaries, you have the barriers, you have the hard lines, and now let's be precise. Let's be close to our argument. Let's try to realize this argument in a very, very systematic way. What's that? That is biological entanglement. This entanglement is very short-lived. And this entanglement in the biological systems is local. It's very local. But it has to be entanglement, a key. And it exists at those molecular scales. It exists at the scales that make up those complex molecules, that make up those complex cells, and they collapse quickly. It does not link brains. It does not link thoughts. It does not link organisms. What it does, it It bypasses the causality. Let's go back to that foggy situation. Let's talk about the foggy mirror. A mirror enclosed by the fog. Imagine that you have a mirror in a fog. You have a mirror, and this mirror is in a fog. And for a moment, for a small scale of time, your reflection is sharp. You can see the image very sharply. And then, as the fog goes on, the reflection, the image that you see it fades. It loses that luster. It loses that clarity. It loses that magnanimity. It loses that symmetry. Now, that moment of clarity, which was there for a very, very small scale of time, that clarity is biological entanglement. And life uses it. Life uses it briefly, I can say. It uses it for very short spans of time, then lets it dissolve. Uses it, lets it dissolve, and trying to preserve it longer and longer, for longer and longer actions. And as it goes, without destroying the functionality of life. So can we say that life is fighting? Why? Why life does not fight? It does not fight decoherence, all kinds of disturbances. We fail to make work of the quantum computer because we want to conserve that decoherence. Life does not attempt to freeze the quantum states, which we try to freeze when we are making a quantum computer. We are trying to freeze it out so that it works. Instead, it works fast. It works locally. It works quantum mechanically. And it accepts the impermanence. What I'm trying to tell is that entanglement is a tool that's used by life. It's not the foundation. Now let's come to the argument of the invisible action again. I'm trying to point out all these arguments to that invisible action. You don't have any cell that understands entanglement. They don't understand it and then do it. They don't understand it. The point is that they don't understand it. No organism independently invokes it. What happens is that it appears. It appears when physical coordinations permit. They permit them to be entangled. And disappears when they do not. So life, I can say that life does not command the invisible action. Life is not commanding it. It is adapting that invisible action. And that action is spontaneously arising from the system. and it adapts around it. Why? Why this discussion? Why this argument? Why this kind of understanding matters for us? It matters because it at least reshapes how we think about living systems. Living systems cannot do it. Life is not merely a bunch of chemical reactions. Life is not merely a bunch of probabilities. Life is not merely a bunch of chances. Life is not accidental. Life is, if I boil down into the chemistry, life is chemistry, constrained and assisted by deep physical correlations. Now, I think I have bored you a lot, but let's close this argument. Let's try to end this argument. And let's deliberate our understanding on it. Entanglement does not make life magical. Everything in life or non-life is magical, everything. You cannot separate one magic from another. Everything is magical. It makes life efficient. It makes life having that peak. It makes life having that maximum amplitude of being there. For a fleeting moment, matter stops acting alone. So what are the outcomes? The outcomes that you have as life, these outcomes align. Uncertainty shrinks, compresses, and the processes that are going on, the processes accelerate. And then the connection that you have among these processes, these connections fade. Or I can say connection fades. And life goes on. Life goes on and on. Life continues. It does not continue by the control. And it does not continue by the intention. But by quietly, smoothly taking advantage. Taking advantage of the deepest rules of the universe, the laws of the universe, the actions on the universe, the invisible actions on the universe. I hope you like it. With this, I would like to end this talk.